We present CAD-SIGNet, CAD language inference from point clouds, using Layerwise sketch instance guided attention. 3D reverse engineering is the process of recovering the computer-aided design process from a 3D scan or a point cloud. A line of works has attempted to tackle this problem by considering the geometry and topology of CAD models from point clouds. However, one crucial aspect of 3D reverse engineering of CAD models is to predict the intermediate design steps. This allows for full editability and reusability of the design while retaining its original functionality. Indeed, CAD modeling is a sequential process where designers draw 2D sketches composed of primitives such as lines and arcs and apply CAD operations like extrusion on them. This sequential process can be modeled as a language. Each CAD step is described as a sequence of tokens, representing either a type of operation or a parameter value. Such representation has been widely adopted for different CAD applications, but was overlooked for reverse engineering. DeepCAD and MultiCAD propose network architectures to infer the CAD language given a point cloud. However, these methods embed the point cloud and the CAD language in different feature spaces, which might result in modality-specific features. In this work, we propose to answer the following question: how to effectively learn CAD visual language representations from point cloud and CAD sequences for 3D reverse engineering. In particular, we propose CAD-SIGNet, in which CAD visual language representations are learned using multimodal transformer blocks with layer-wise cross-attention. CAD-SIGNet follows an autoregressive strategy, allowing for interactive scenarios of reverse engineering. CAD-SIGNet also leverages its autoregressive nature within a sketch-guided attention module that focuses the multimodal transformer blocks on relevant regions of the point cloud. We will now describe the proposed approach. Starting with the CAD language formulation, our representation is composed of two main components. The first one, 2D sketch, is described by a set of faces, loops, curves, and point coordinates. The second one, extrusion, describes the transformation of the sketch into 3D space, its scale, and the amount of extrusion. These components are represented by a sequence of tokens. In particular, each CAD design step is represented by a sequence of tokens for an extrusion, followed by the corresponding sketch token sequence. As for the proposed architecture, CAD-SIGNet is an autoregressive model that learns the next CAD sequence token given a partial sequence and a point cloud. Firstly, the point cloud and the input sequence tokens are embedded. One of the main components of the network is multimodal transformer blocks that take as input the point and token embedding and perform cross-attention between them. Within each block, the point embedding are further encoded, and the CAD sequence embedding are processed through multi-head self-attention layers before the cross-attention. In order to capture fine-grained details of the sketches, a sketch-guided attention module is introduced. We posit that parameterizing a sketch requires only cross-attending to a subset of the point cloud. Thanks to the autoregressive strategy, the predicted extrusion tokens can be leveraged to define a sketch instance on the point cloud. This way, the cross-attention for sketch prediction involves only the inferred sketch instance. Finally, the embedding are passed through a MLP to predict the next CAD sequence token. At inference time, we propose a hybrid sampling that allows for 5 different CAD sequences to be proposed. The final CAD sequence is chosen by selecting the one that results in a reconstructed CAD model with a minimum chamfer distance with respect to the input point cloud. Due to its autoregressive nature, CAD-SIGNet solves a range of 3D reverse engineering problems, such as the full design history recovery from an input point cloud, conditional auto-completion, and user-controlled CAD sequence generation. The qualitative results on a full design history from point clouds show that CAD-SIGNet outperforms DeepCAD baseline on both the DeepCAD dataset and in a cross-dataset setting using the Fusion 360 dataset. This observation is further validated from the quantitative results. CAD-SIGNet is also evaluated in a conditional auto-completion scenario in which a partial sequence and a point cloud are used as input to predict the complete CAD sequence. We observe that CAD-SIGNet outperforms the adapted SkexGen and HNC baselines. Finally, we also conducted a cross-dataset experiment in which the point clouds are obtained from realistic 3D scans of the CC3D dataset. CAD-SIGNet clearly outperforms DeepCAD baseline on this setting. Thank you for listening. You can learn more about CAD-SIGNet by visiting our project page.